Okay, problem number 12. We're given a data table of velocities here. Velocity of a car in miles per minute, given in the chart below. And we want to approximate the integral from 0 to 30 of the velocity function using three equal subintervals and the trapezoid rule. And we need to think about units here. Now, I'm a visual learner. I like to see things. So what I'm going to do is I'm going to draw just like a teeny tiny little graph here representing this situation. So I'm going to do 0, and then I'm going to do all these time intervals. And so I'm going to go through and just roughly plot each of these points. So at 0, I'm up at 0.5, so I'm right there. At 5, I'm at 0.8, so I'm just a little shy of there. And 10, I'm up at 1, so I'm a little bit higher now. 15, 1.2, a little bit higher again. And then 20, I'm up at 1.25, so all the way up there at that fifth tick mark. Then 25, back down to 1.1, so a little bit lower right there. And then finally 30, I'm down to 0.9, so something right like that. Now again, it doesn't matter if you're perfectly to scale. The idea here is we are doing a trapezoid rule, and we're splitting it up into three equal pieces. So we need to be using right there. It's going to be one of our trapezoids. Next trapezoid is going to be from 10 to 20, right there. And then the last one from 20 to 30. So there are our trapezoids. Notice that the height of each of these trapezoids is 10, because the subintervals are equal. And so we're going to approximate this by writing an equation. So if you think about the area of a trapezoid is the average of the bases, b1 plus b2, times the height divided by 2. But our height is the same for each of them, and we're going to be dividing each of them by 2. The height is 10, so we're going to get 10 divided by 2 is 5. So really our area is going to be the bases added together and multiplied by 5. So let's look at my pink trapezoid. I'm going to get height of my bases. So I'm going to use the y values of the left endpoint there. So the y value of 0 is 0.5, plus my second y value there at 10, which is 1. And now I am going to be adding all of that. So I'm just going to go ahead and do what I know about. Okay, fine, I'll show you this. So let's go back. We're going to say that was going to be multiplied by 5, the 10 over 2. And then we need to add to that the green area. And so we're going to get that first y value, which is at 10, which is multiplied by 5. We're going to get 1 plus the second y value there at 20, which is 1.25. And then we need to add to that our purple triangle, which again will be multiplied by 5, times that first endpoint, which is the last one we used, 1.25, plus that last endpoint, which is 0.9. Now notice what we're doing. We're multiplying each thing by 5, so we can factor the 5 out of all of that and just say 5 times that right there, 0.5 plus 1 plus 1 plus 1.25 plus 1.25 plus 0.9, which I can actually write even simpler. I can say 5 times 2 times 1 plus 1.25, because notice 1.25 is twice and 1 is twice, because those are shared. And then I need to add my singletons, which is 0.5 and 0.9. I don't know, maybe I'm making this unnecessarily complicated by making it simpler, but there's an equation right there that should represent that approximation. And you should end up with, you should end up with 29.5. And we're finding the area underneath a velocity graph with respect to time. So we're integrating velocity to get position. If our units here were miles per minute, that means we have now traveled in 30 minutes 29.5 miles, which means this dude's going pretty quick, actually. So that's that. Now let's go ahead and do part B. Approximate it using 3 equal subintervals and the midpoint rule. Okay, so we're again going 3 equal subintervals, so we're going to have those same intervals, 0 to 10, 10 to 20, 20 to 30, but now we're doing a midpoint rule, which means instead of trapezoids, we need to use the height of the midpoint between our boundaries, which means we're going to be using that x value there at 5 for that first rectangle, and I'm sorry, the y value there, and then the y value at 15 for the second one, boom, and then the y value at 25 for the third one, and then these are the rectangles we're dealing with. So let's find the area of those rectangles. Area of a rectangle is base times height. All of the bases there are 10, so this is going to be, the area is just going to be 10 times whatever the height is for each one. And we're going to add all those areas together. So we're going to get 10 times that first height, which is the y value of 0.5, the y value of 5, which is 0.8, plus 10 times the y value at 15, which is 1.2, plus 10 times the y value at 25, which is 1.1. So again, we've got some distributive property here where we can say this is 10 times the sum of all of that. So 0.8 plus 1.2 plus 1.1. So we can do this one in our head. 0.8 plus 1.2 is 2, and then add 1.1 to that, we'll get 3.1, and so we'll get 3.1 times 10 is 31. So with this approximation, we are determining that we've traveled 31 miles. The trapezoid rule determined that we traveled 29.5 miles, so pretty close, but a little difference there. Which one's more accurate? Hard to say. We could use even smaller intervals and get an even better approximation. My dog is crying, so I'm going to go. Important thing to remember here is that we're integrating a velocity function in miles per minute, and that is getting us a position function. So we've determined how far this car has traveled between time 0 minutes and 30 minutes.